Today we have the same program as yesterday, but instead of Boris, Doran will start at 3:30, I think. And then afterwards we have again the discussion session. You already know how this works. Okay? So I got told that yesterday I was going a little bit fast. Is this correct? No. Too slowly? We will see. So we have lecture 2. It's fantastic to have the first lecture in the morning because you have a clean blackboard. I really enjoy this. And this will be ring maps. So all this is only preparation and mostly kind of linear algebra or commutative algebra. So you will have R and S will be commutative rings as always. And mostly they will be K algebras. And then we may have all the nice properties we may wish. So the Noetherian, sometimes they are local, and so on. And maybe they have some topology, maybe this topology. So we have seen yesterday the thematic topology on the space of formal power series. So you should always think of, you just take the polynomial ring, or you take a localization at the prime ideal or at the maximal ideal. You take a ring of convergent power series, or you take a ring of formal power series. And then we will also have, a little bit later, the ring of algebraic power series. Okay? And we look at ring maps R to S. So these are linear and multiplicative. Linear plus multiplicative. And actually, as everything will be K algebras, they will be K algebra homomorphisms. K algebra homomorphism and whenever we have some additional information, for instance, if R and S are local rings, we want this map to be local. So if Rm Sn are local, then maybe we call this F. Then F should map M into N. So this is what is called a local map. F local. And then, of course, if this holds, you will have F of M to the K inside N to the K, trivially, which implies that the topologies correspond to each other. So this condition here just means that the map F is continuous with respect to the m-adic and n-adic topology here. F continuous with respect to m-adic topology on R and n-adic topology on S. Please check yourself that this is just the continuity property. Okay. So saying that the maximal ideal goes into the maximal ideal is the algebraic condition, but you can also see it topologically. Okay. So let me start with R. So example. R K Y1 Ym S K X1 up to Xn. This is a situation of algebraic geometry, which will not be our situation later on, but it's good to motivate. So if this is a K-algebra homomorphism, then it is prescribed by the images of the generators. K-algebra homomorphism is given by the images of the generators y1 ym of R. So these are f of yi, they are elements of S, so they are just polynomials in X. F of yi, I don't know how to call them, maybe let's call them ji x1 to xn polynomials. Okay, gi and kx. And whenever you have, maybe I write p of y1 up to ym, some polynomial in R, I guess you are all familiar with this, then the image of this is just given by substitution of the variables by the polynomials gi. P of g1 of x, gm of x. Okay? So this is just the substitution homomorphism. Okay? And it's easy to see that all are of this type. So actually, what we conclude here is that the ring map F is given by a vector of polynomials. Ring map F corresponds to a vector of polynomials g1 gm in kx to the m. And I will always identify vectors of such elements with the associated map. Okay. So now you may look at maximal ideals. If we take M, the ideal generated by y1, ym, again we have to distinguish between the German M and the index M, and N x1 xn, then you may want that f of m is contained in n. This would be again the continuity property is equivalent to gi belonging to n for all I, which just means that gi vanish at 0. Gi of 0 equals 0 for all I. Okay? Then you would say this map F respects the topology induced by M and N. So I started from the ring side, but now you can get, of course, a geometric map it goes in the opposite direction from k to the n to k to the m. I write again x1 up to xn for the points, go to g1 of x, gm of x. Okay, so this is the kind of dual map. Usually you start with this type of map and you go to the ring homomorphism, but we are more on the algebraic side, so we start with a ring map. Boris, could you bring me a glass of water from outside, please? Be so kind. Thank you. So we are not really interested in the polynomial ring. We are interested in the more difficult rings, the power series rings. Now, if you take R, K, Y1, Ym, and S, K, X1, Xn, and F from R to F. Thank you very much. If you take a ring map, now here these are local rings, so you'll immediately ask that the maximal ideal ends up in the maximal ideal here, local ring map. Then the situation is a little bit more complicated. You want to say that again this is determined by the images of y1 up to ym. And that's not completely clear, because knowing that this is a K-algebra homomorphism, so let me write it again. What you will get is that all the products of the yi's and all the sums of the yi's are determined by these images. So you will get that all polynomials in y1 up to ym are determined by these images, but you don't know anything about the power series. So if you're given fy1, fym in kx prescribes f restricted to y1 up to ym. You get it on the polynomial ring, which is a subring, but you don't get it yet on whole R. Okay. So there's a delicate point here. By K-algebra homomorphism, you just can extend it to here. But now you use the following. As f sends m to n, we said that this will be continuous. Now the polynomial ring is dense in the power series ring, and then you have a unique extension to R. So let me write this down. Note ky in ky is dense for the M-adic topology. So this, let me call it f tilde or f0 maybe. So f0 admits at most one extension, and then it's clear how you define it. Therefore, the extension of f0 to k to the power series is unique. By continuity. Okay. So again, we can say, therefore, any f from ky to kx local or continuous is again given by the images fyi for all I, hence by a vector g1 of x, gm of x in kx to the m, and the condition of locality or continuity just says that these gi have to vanish at 0. With gi at 0 equals 0. And now if you take any power series in y, if h of y1, ym is in k, y, then the image of h f of h is just h where you substitute g1 of x. So it's precisely the same as before. You substitute in a power series a vector of power series. Okay? And this is well defined because these have no constant term. Thomas.
Can you give me a non-local morphism between those two?
This is a good exercise. I wanted to put it on the sheet. Actually, all are local.
Yeah, which are well defined. Which are well defined everywhere. Yeah.
So, if we go back now to geometry, we don't really have a space behind these rings, but I still want to put a space, so I will write the following. Geometrically, we would have k, here we have n variables. Now, as the maximal ideal plays here a specific role and corresponds to the origin, I will write here kn0. So scheme theoretically, this is the scheme of this ring, but you don't have to. So this is not really a map, it's just what I call a formal map. Everything is given here, but x1, xn goes to G1 of x, Gm of x. Okay? So these are kind of formal germs, if you want. Formal germs. It makes sense to talk about these in the convergence setting if R is K y1, ym, so K could be complex numbers or real numbers, K x1, xn, convergent power series. Then you can really talk about maps, and then the geometric maps map. Then you have here G1 up to Gm will be convergent power series. So they will be defined on an open neighborhood, Euclidean neighborhood of 0. And you get something like U in Kn. So this is open, but take care in the Euclidean topology to Km, and this will be an analytic map. Analytic, or in the complex case, holomorphic map. And again, it just has these M components. So what is the inverse function theorem? This works faster like this. So in this setting, we know what the inverse function theorem means, and we will now go back to the formal setting for ring maps and define it there. So inverse function theorem so we can identify the ring maps in these specific settings with vectors of power series. So let me check my notation. Yes. Now I write instead of G more dot. Let me write it like this. Let F in K, maybe we do it in the convergence setting to simplify the intuition. So now we take a vector of power series, be a vector of convergent power series. Recall that this corresponds to a map from Kn. Now I just write it like this to Kn. Now we have on both sides the same dimension, and I just abbreviate this like this, saying in some neighborhood it is defined. We assume that f of 0 is 0. This just means that the induced map is local. Yeah, you have to go back and forth to see this. And now the assumption will be on the derivative. df will be dfj dxi, the Jacobian matrix. And we assume that the determinant of df at 0 is non-zero, so the matrix is invertible. then there exists a G in Kxn, G of 0, 0, such that F composed with G is just x1 up to xn. So what does this mean? F has n variables x1 up to xn and n components. So this is f1, g1, gn. Everything is now vectorial, g1, gn. It is a vector of convergent power series, and the statement is that we can get back the identity. Okay? And the remark is this also holds over Kx, so for the formal power series, and also for Kx, even though we haven't defined it yet, the algebraic power series. Okay. So I will give you the proof, or the idea of proof in this setting, and I will do it only in the formal setting. So F is a vector of power series. So write F. Now these are just power series. They will start with a linear part, L plus H, L linear part, and H. Now H is a vector of n components. And these are power series that will all have order at least 2. Order of Hi at least 2. And the assumption on the Jacobian matrix, so now if you derive and you set x equals 0, you will just get the linear part. Okay, so the assumption is L. Now L is a vector of L1, Ln in Kxn, a vector of linear polynomials. So this defines an isomorphism. Yeah? Defines an isomorphism. You can see it on the level of ring maps. You can also see it on the level of linear maps from Kn to Kn. Okay? I leave the details to you. I just want to give you the main idea. Okay? And you want to show that F is an isomorphism. This is something similar to yesterday. Yesterday we had something isomorphism plus something and wanted to show that the plus something is again an isomorphism. But now H is no longer linear. So there is a substantial difference here. But the argument is a little bit similar. So I can compose LF with the inverse of L. Yeah? And then I can make L to the identity. So replace F by F composed with L inverse. You always have to make clear what I mean by the composition. But that's up to you. And assume L is the identity. And you define the inverse recursively. Construct G equal F inverse recursively. it starts like in the linear case, the geometric series. So you take G0, identity minus H. This is how you would start in the linear case. But then Gk plus 1. Now all this is vectorial. Is the identity minus H composed with Gk. Correct? I always forget it. Yes. So these are now vectors. Instead of x, you could also write x1, xn minus h1, hn. Okay? And here again. So these are vectors of power series. And you have a rule to construct one step to the other. You have an algorithm. This is actually the Newton algorithm here, if you look at it. And then you take G, the limit of Gk as k goes to infinity. And this will be, I did not put it as an exercise, at least this will give you a formal power series. It's not very difficult to show that this is a vector of formal power series. Another exercise I forgot to put on the new sheet. So we have already proven now, and it's clear, easy to show, that F composed with G is the identity, which means x1, xn. You just compare. You plug in Jk plus 1 and you immediately get that this is a formal inverse. So G is a formal inverse. Okay. What about convergence? We would like to have G to be a vector of convergent power series in case that F, the vector here, is convergent. So now we really have to prove something. That's not so easy as the geometric series, because now you see this algorithm, it's nonlinear. H is nonlinear. Yeah? H is nonlinear. But you can look at this equation. You know already that G is unique. And here F is convergent. This side is convergent. So you can apply Artin approximation as Guillaume explained it and deduce that G is convergent. I repeat, F is convergent. X is convergent. This is just substituting. Yesterday you wrote Y instead of G. So as it is unique, it must be convergent.
But there is a problem. I'm afraid you only use this proof the implicit functions.
Hopefully.
Which is wrong.
That's where I wanted to go, yeah? To use a theorem where I will need this theorem. Okay? So I didn't want to cheat you. I just want to say you need a different proof. Yeah? But I'm not going to do the convergence. It's not very difficult. Again, you have to use these Banach spaces. So instead of quoting Artin, so prove convergence of GI by norm estimates. in the Banach space KXR. You use again these spaces which I introduced yesterday. Okay? Or you can use the Banach fixed point theorem. But here you really have, here is some analytic part you have to plug in. Okay? We don't need it now, but I just want to point this out. And let me now formulate the implicit function theorem. Which is very similar in spirit. Now you take, I always formulate it in this setting because this is very concrete and explicit. Now we take f in kxy to the m. So x is x1, xn, y is y1, ym. So we have as many components as the y variables indicate. Again, we assume, as always, f of 0 is 0. And now we just take the derivatives with respect to y. dyf will be dfj dyi. So this is now a square matrix. This is an m by m matrix. Assume the dy of f0 is invertible, so determinant is non-zero. How do I want to formulate it? Then there exists an automorphism phi of kn plus m0. So this is again convergent or formal according, let me write here convergent. So what do I mean by an automorphism? We already have seen the inverse function theorem. These maps here are just automorphisms of k to the n at 0. Yeah? We have characterized the automorphisms of k to n. So maybe you add here f is then an automorphism of kn0, say, now here automorphism in the sense of biholomorphic or convergent, say an automorphism and k-algebra automorphism of k x1 xn. Now, this is confusing, but I ask you to unconfuse it at home or here. I'm identifying now vectors of power series with maps from kn to kn, as we did before, and with the k-algebra automorphisms here. Okay? I just explained it before that we have all three ways of describing maps. Yeah? So think about it. And if there exists an automorphism in the sense as before, such that f composed with phi is f of x0 plus y. So phi consists of n plus m components, so this is again the same notation as before. So what it says that a priori f, maybe I give you an example. It's not possible to understand this without sitting down and writing down what is meant, but the example would be you take just n equals m equals 1, and you would take just one power series f of xy equals x squared plus y squared plus x y cubed. You had these examples yesterday in the exercises. Yeah? And the statement is that you are able to replace, actually it suffices to replace y so that you can eliminate all this. F composed with phi of xy will be x squared plus y. And once you have made it linear in y, you can solve for y. Okay? If you want to equate it equal to 0. I'll come back to this tomorrow because we will need it. Now the implicit function theorem is an easy corollary of the inverse function theorem. So I of t is equivalent to I of t. So here I mean that's not very good. I n of t, I m of t. You know what I mean. Okay. So in algebraic geometry, we only have polynomial rings. We have, let's say, f, now a polynomial vector. F of 0, 0. If f is a polynomial, yeah, in the algebraic geometry you only work in the category of finitely generated algebras. And if I'm back now to the inverse function, so dy of f of 0 invertible, then you can interpret f as a vector of formal power series, and you can apply the inverse function theorem to construct a formal inverse where there exists a g in kxn formal power series vector, g of 0 equals 0, with f composed with g is x. But g is not polynomial. So you don't have the inverse function theorem in algebraic geometry, as you know. But in general, g is not a polynomial. But you don't want to go to the formal power series rings for certain reasons, because it's, as Guillaume already indicated, this is a rather huge ring, and the answer to this drawback is that you look for the smallest ring where this G exists. Try to find a smaller ring, and I will already denote it like this, inside Kx, where I of t holds. maybe I will need this. And this will lead us to the concept of algebraic power series. So I'm not going to do it in the all generality. Again, we will stick to the case which is interesting for us. So this is the next section, algebraic power series. So this will be now the following inclusion of rings. We have the polynomial ring in n variables. We have the localization. Here we will have the object we want to define, the ring of algebraic power series, and these will ring of algebraic power series. Okay? And for this we will do Hensel's lemma. So I will only do it in the setting of convergent power series, but it holds more general, only for R kx1 xn. So we take a new variable t, let t be a new variable. So Hensel's lemma in version 1 is something like the implicit function theorem over there, but with just one additional variable, which I now call t. Let t be a new variable. Let p of xt in kx t a polynomial. In t. So you know that the implicit function theorem tells you something about the existence of solutions, and this is a statement of the Hensel lemma. So we assume that two assumptions assume if you set t equals 0, so this will be the constant term of the polynomial, then this lies inside x, which just means that p 0, 0 is 0. And then we will derive p with respect to t. So p prime of xt will be the partial derivative of p with respect to t, just one variable. And we assume that at 0, p prime x0 does not belong to x. So this means p prime of 0, 0 is non-zero. You will see the parallel to the implicit function theorem. And the statement is that then there exists, maybe I write it here, a of x in kx such that p of x, a of x 0, a 0, 0. So this is the existence of a solution in the case where the implicit function theorem applies. So homework, compare this with IMFT. I don't have time to make it explicit, but you will see that it is precisely the same statement, but just in one variable, and where you take for p just a polynomial in t. So this is Hansel's lemma, and the ring of convergent power series satisfies this lemma. It's not very difficult to show. It's essentially the implicit function theorem. Also, the ring of formal power series does this. So such a ring is called Henselian. So, definition. Rings, local rings satisfying this lemma are called Henselian. Though in some sense Henselian rings are the local rings where the implicit function theorem in one variable holds. Hensel lemma 2 the usual version of the Hensel lemma is with factorization of polynomials. So you take again p in kxt polynomial, and now you assume that you can factorize it modulo the maximal ideal. So monic polynomial in T assume that P factorizes modulo x, which is the maximal ideal of our ring. So P is P1, P2, but just, do I want to call this P1, P2? Yeah, mod x. And you want in the factorization that P1 and P2 are co-prime with P1, P2 co-prime. Then there exists a factorization P equal Q1, Q2, which is a lift of this factorization, which means that the residue class of Q1 mod x is P1 and so on. Lifting P equal P1, P2. So lifting means Q1 modulo x is just P1. Okay? So this again is a kind of Artin approximation for factorizations, as Guillaume explained you yesterday. And these two are equivalent, which is not very hard to see. Okay, so this is a classical way of defining Hansel's lemma, but I never understood this until I saw this lemma, which was relatively late. So I think this is easier to memorize. Okay. Now, Nagata did the following. He just took all the rings which satisfy these lemma. So if Rm is a local ring, there exists the smallest extension R inside RH. The Henselization of R for which Hensel's lemma holds. Okay. So this is now something more precise than the formal power series. If you start, so think of R be the localization of a polynomial ring. Then instead of going to the formal power series ring, which is huge, yes, Guillaume?
Maybe you should mention that in answer lemma 1 and answer lemma 2, the liftings and the solution are unique.
Yes, thank you. Unique.
Boris asked me the question, so it's perfect.
Okay. In any case, you will find more on this in the notes. So, instead of passing from here to the formal power series ring, we go to this smaller extension, which is the Henselization, and this Henselization will have better properties. So if R is Noetherian, also RH is Noetherian. This is just a side remark. But the important thing is, how does RH look like for this one? So now we use a new blackboard. Theorem. That k x1 xn denote the algebraic closure of kx x inside k x1 xn. So these is a ring. I make it explicit. The ring of formal power series H1 H of x1 xn in kx, satisfying a polynomial relation a d of x hd plus a1 of x h plus a0 of x equals 0 with ai of x polynomials or polynomials. So we take what we already introduced, the algebraic closure of the polynomials inside the power series rings. The elements are called algebraic power series. Often they are also called Nash series, whatever you prefer. And the theorem says that this is the Henselization of the localization. Then kx equals kx xh. So this is a different description of the ring of algebraic power series. It is the smallest ring where the inverse function theorem holds. So let me write this down. Therefore, therefore, Kx is the smallest extension of Kx. You can either take the Hansel lemma, but you could just say where the IFD holds. Okay. Now, this ring of algebraic power series has nice properties, though I will put it here without explaining for the moment. The fact is, for those who are familiar with inductive limits, Kx is an inductive limit of finite etale extensions of Kx. So in the second half, I will talk a little bit about extensions of finite extensions and etale extensions, very briefly, but we will need a little bit. So maybe I should give you two examples just to clarify a little bit before starting with the other stuff. Example, and this will be on the exercise sheet. As we saw yesterday, 1 plus x is algebraic. Second, any algebraic series over R or C is convergent. So this is not so easy. A proof can be found in the book of Pfister de Jong. And you only understand the definition if you have an example of something which does not satisfy the condition. So what is a series which is not algebraic? You're sure? That's not very difficult because you can just put x equal to 1 and then use the transcendence of E. What about this example? 1 plus x squared plus x4 plus x18 plus x16 and so on. Boris is smiling.
It depends on the so on.
It depends on?
On the so on. On the dots.
32, x64, and so on.
He wants you to write sum of x to the
You can choose the continuation you want.
No, it's not.
Of course, you could just add the exponential here to make it not algebraic.
Depend on the basis.
Depends on the characteristic.
Depend on the basis.
A little bit. So characteristic, let's say, or different too. So let me call this h of x. So an exercise I forgot to give you.
Because you mentioned I think you should mention also in the sample one.
Here, yes. I will always specify the characteristic afterwards. Thank you. Yes. So here this is also transcendent. So small homework. Compare h of x and h of x squared. And you will find a functional equation for h. But it's not this type of equation, it's a more complicated equation. Yeah? But still there's an equation behind. I think Boris can tell you more about this type of phenomena. Okay, so what's the time? Where is the... Aha. When do I have to stop at half? Very nice. Impossible. Yes?
So in the first example, the characteristic not equal to 2 is only important because the square root is not a power series, or but we still for the formula 2 takes the square root and the joining product.
The square roots in characteristic 2 do not make sense. I don't want to discuss it here. So now, Dorin, what would you need this afternoon? You need etale, you need finitely present? Smooth. Okay. Let's go for it. So this was a section on algebraic series. I'm sorry that I'm kind of quick, but I cannot cover everything. Smooth, unramified, etale ring maps. So this is a 2-semester class, which I will do in 20 minutes. So I give you a definition which is not to be understood. Let RS be a ring map. And afterward I will give you a geometric interpretation which helps you to have an intuition. It is called formally smooth, unramified etale if for all rings R, Rt, for all ideals J in T with J square equals 0, for all commutative diagrams, for all diagrams. So now we take ring maps between R, S, T, and T mod J. So whenever an arrow is drawn like this, it's part of the given situation. So you assume that you have given a diagram like this, with this strange property that J square equals 0. And then you ask, so this T to T mod J is just the canonical map. This here is F. This is the canonical map. And here you have given some ring maps. And then you ask whether you have a lift of this map here, alpha. So this is dotted. And the conditions are for smooth there exists at most one alpha. At most one map alpha. For at least for unramified there exists at most one map alpha, and for etale there exists precisely one map alpha, making the diagram commute. So this is a formal definition which is useful for proving, but you don't have to understand it. I don't understand it, but of course you are allowed to understand it but I will never understand it. So typical would be you take for T something like KT mod T square, and for J the ideal T. This would be a situation where you can think about it. Instead of going into this, I will give you a geometric interpretation which is coming from differential geometry. And I think these geometric interpretations help you to keep in mind what this means. Differential geometry. And we take a very simple setting where we just have Rn. So F from Rn to Rm is the infinity map. So these concepts here are just the algebraic counterpart of what I'm doing here. Okay? I cannot give you the relation, but I will at least tell you what corresponds to what. So you take A point in Rn, B the image of A in Rm. Then you have df at A, the Jacobian matrix, d fj dxi Jacobian matrix of f at A. And this will define the tangent map TAF from Rn to Rn. V goes to V times dFA. This is the tangent map of f at A. And then you have three concepts in differential geometry. The first one, f to be a submersion at A. F is a submersion at A if and only if the tangent map is surjective. TAF is surjective, which just means that the rank of the Jacobian matrix equals m. M is the dimension of the target. This is the concept of submersion. I hope you are familiar with submersions. And this is equivalent, now, if you translate it accordingly, to smooth. F is smooth at A. Okay? So being smooth corresponds to submersions. F is an immersion at A. TAF is injective, which means that the rank of DFA is precisely n, and this corresponds to being unramified. F is unramified at A. And now you can already guess what it means to be etale. It's amazing how little material one can do in 1 hour and half an hour. So if the tangent map is an isomorphism, which means that F is a local diffeomorphism at A, then this corresponds to etale. So F is submersion plus immersion. F is a local diffeomorphism at A, which means that TAF is a linear isomorphism, which means that the rank, that n equals m equals the rank of DFA, then this corresponds F being etale at A. Okay? So the etale maps are those which correspond to diffeomorphisms. So watch out, 2 remarks. First, whenever you have a submersion, the fibers are smooth. If F is a submersion at A, so if it is smooth in the sense of algebraic geometry, then the fibers F inverse of C for C close to B, which is F of A, are manifolds. Actually, even stronger, even a local diffeomorphism in Rn at A, let me call it phi, and now you may see how everything relates. A local diffeomorphism phi in Rn at A linearizes F, which means if you compose F with phi, And then, how do I call x1 up to xn? Up to a coordinate change, f becomes linear. And as it is linear, it is just xm, and m is less than n. So this is a very strong statement. It gives you a normal form of these maps. So phi will be RNA to RNA, a local diffeomorphism. And something similar holds in algebraic geometry. Okay? So when you can linearize, the fibers are automatically manifolds. Okay? So this stronger statement implies this first one. And second, if we now take a polynomial map, let f from kn to kn be a polynomial map, so it's just given by a vector f1 fn fi in k x1 xn. And to simplify, we take A the origin, A0 in Kn, f of 0, 0. And we assume the condition from the inverse function theorem, assume that df0 is invertible, with invertible matrix, then f is not yet invertible because the inverse is not polynomial. Then f need not admit a polynomial inverse. Then f is etale at A equals 0. So the invertibility of the Jacobi matrix is equivalent to being etale, so you can easily check for maps like this whether it's etale, and the induced map on the formal power series ring and f star from k x1 xn to k x1 to xn, g goes to g composed with f. If you take instead of the polynomial rings the completion, the formal power series ring, then this map is an isomorphism, is a K algebra isomorphism. Okay. And this actually is a way to characterize smooth, unramified, and etale. And what you should keep in mind, the take-home message is, so philosophy etale map between local rings becomes an isomorphism after completion. And vice versa. So the etale maps are those is a substitute for the failure of inverse function theorem, but if you pass to the completed local rings, then it works. So if you have R to S, F, local rings, and then you have R hat and S hat, and here you have the completed map, then F, actually it's an equivalence, F is etale. So this is a map of local rings. And for smooth and unramified, you can do the same thing. F etale, if and only if F hat is an isomorphism. So this, of course, is a lot of material. You don't have to understand everything to understand Artin approximation, but it gives you a little bit the background where one is working. So, yes.
This is a small problem. Here, etale to you is an etale neighbor. This is.
But so that's why I have talking about local rings. Yeah, of course.
But it's the same.
Yes.
Do you need materiality for this equivalence? Do you need materiality for this equivalence?
I don't think so. No, this is just a general effect, I think. Yeah? No. So that's...
But you need to see the
Yes, but I don't want to talk about residue fields here. Yeah.
That means etale at the point A.
Yes, all this is local at the point. Yeah. You can also extend it, but then you have to look at all the points, and the notation becomes smaller.
We only find it for some rings. That to be etale, but that means F is etale at the point A.
Yeah, either you say F is etale at the point, or you start from the very beginning with a map between local rings, because these specify a point.
Okay. The localization of the point.
Yeah.
You take this as your...
So I would propose to you not to go to Grothendieck and study etale topology or to the text project. Go to differential geometry and try to understand submersions, immersions, and the inverse function theorem. Okay, thank you for your attention. Tomorrow we will do a little bit about flat maps, flat ring maps, and then we will do Artin approximation in the linear case. We will prove it and start with the proof in general, with a different proof, and Guillaume will start today at 11 o'clock. Thank you.